also going to be, I will be recording these lectures and I'll be uploading them to our YouTube channel so you can watch them later. They're usually up and ready within a couple hours. So that's kind of my idea. Okay, so back to it, least common multiple. So let's say you had two numbers, and let's make them interesting numbers. Let's say you had 7 and, oh, I don't know, how about 5? You have 7, you have 5. You want to find the least common multiple of those two numbers. Well, start by listing the multiples. That's my attempt at a colon. So let's think, the multiples of 7. 7, 14, 21, 28. You might need to list maybe 6 to 9, somewhere in there, multiples. 35, 42, ... 49. Now let's list out the multiples of 5. Yeah, 5, 10, 15, 20, 25, 30. Might need to give myself a little more space here. Microsoft Paint, good old Paint. Never let you down. 35, 40. So I've listed out the multiples of our two numbers, and we're going to see that this is kind of the simple way of doing it. And now we look for it. Literally, it's exactly what it sounds like. Least, meaning the smallest you can find. Common, meaning both of them share multiple. So what does it look like it is? 35, exactly. Bada bing, bada boom. Now, the 35 happens earlier when you look at the 7's multiples than it does with the 5's multiples. That doesn't matter. It's just which is the smallest one. Now, if you were to keep going on with 7, you'd go to 42, 49, 56, 63, 70, 77, 84. If you kept going on with 5, you'd have 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. You'll notice then you'll see a 70 in there. They also share a 70. So you can have more than one common multiple, but 70 is not the smallest possible one. We want the least common multiple, which would be 35. Now, let's pick maybe some more interesting examples. And we might have to strain our brains a little bit with the mental math on this. Let's find the least common multiple of 15 and how about something a little bit interesting? How about 20? 15 and 20. Now the numbers are a little larger, so you might have to do a little bit of extra mental math, a little extra heavy lifting in your mind. Let's see, 15, then you just keep adding 15 as you go, or you can multiply by the next number. 15 times 1 is 15. 15 times 2 is 30. 15 times 3 is 45. 15 times 4 is 60. Then you get in 75, then 90. Theoretically speaking, how long could I keep writing that list? Forever and ever, yeah. I can keep going and going and going and going. So at some point, I just have to say, okay, maybe anywhere from 6 to 9 multiples is plenty. For 20, and you're just hoping you're going to see a common multiple in there. If you don't, you're going to have to keep going. You're going to have to keep going and going. But we get lucky. 60. 60 is the least common multiple. You can write it LCM of 15 and 20 is 60. Bada bing, bada boom, that's not so bad. not so bad. There's another kind of method to finding the least common multiple that is very similar to how we found the greatest common divisor last time. If you remember, for a specific base, say 2, the first number had 3 2s, the next number had only 2 2s. For the greatest common divisor, you take the least number of representations. So it's really weird because greatest common divisor, least number of representations. For the least common multiple, you switch it. If one number had 3 2s, the other number only had 2 2s, the least common multiple would actually take 3 of the 2s. It would take the most amount you can possibly get. So we're not going to go over that method in detail because it's not super horribly interesting, but you can always keep that in mind. So let me queue up our next round of information. Okay, so we're going to talk about integers, and we're going to talk about order of operations. Now, the cool thing about the integers, so last time we learned about the natural numbers, and we pretty much said, hey, the natural numbers are all the positive whole numbers, 1, 2, 3, 4, 5, 6, 7. But wait a minute, Josh, we can't forget about those negative numbers. Negative numbers are very important. A negative number, depending on the context, can mean a loss. If you're a business, you go out there and you sell corrugated sheet metal, well, you might be interested in knowing whether or not you pulled a profit, right? Because this is America, there's only one thing that's important to us, and that's making money, all right, and making a profit. So a negative number could represent then a loss that you spent $2 million on your business, but you only brought in 1.5 million in revenue. You didn't bring in enough, you lost $500,000, which means that's, how do you have negative money? Well, it means your investors, the people who gave you money to get your business going, they're not going to be getting their money back as soon, something like that. So negative numbers are very important. So as you can see, the integers, they have the positive numbers in there, 1, 2, 3, 4. They have 0 in there as well, and they have the negative numbers. If you're curious, the integers have a cool sign all of their own. It's a weird Z-looking thing. Remember last time we said the natural numbers, the positive whole numbers, they had their own sign. The integers also have their own sign. As well. That's me drawing with my finger, but we are doing it, we're getting it done. Now, what this means for us in general, we have something called the number line. The number line, and it ain't lying to you, and if you like that joke, I apologize in advance because you're going to be hearing a lot of those kinds of jokes. And if you like it now, you won't like it in about a week. So you're just going to have to get used to it, okay? I'm a little bit of a humorist. Doesn't mean I'm good. The number line looks like that. It's where we put the numbers, obviously. But now notice as you go down to the left, numbers go -1, -2, -3, -4. So they get more extreme as you go to the left. As you go to the right, they get more extreme as well. What do I mean? Well, we know 1, then 2, then 3. But if you're going backwards, you have to do a mirror image flip around the number 0. So 0 is kind of like an anchor for them. And that does get a little bit confusing. That does get a little bit confusing. So if we think about it, you can graph -3. When you're graphing just single numbers, you're just putting them on a single number line. That's all it is. So if you wanted to graph -3, there it is on the far left. Let's see, do I have a pointer? I don't. I can use my mouse. You have -3, there you go, on the far left. 0 is right there in the middle with Malcolm. 4 is over here on the right side of things. So if something's positive, if you have a positive number, every positive number is greater than every negative number. The number 3 is greater than all negative numbers, all of them. Simply because 3 is to the right of, say, -2, -3, -4, -5. 3 exists to the right of them, thus it is greater than those negative numbers. In fact, we formalize it and we use the actual symbols. We use the less than symbol, the greater than symbol. And we can talk about what it means to be less than, what it means to be greater than. Basically, any number which is to the left of another number on the number line is less than it. So you can see here, -4 being to the left of -1, that makes it less than -1. We talk about the positive numbers 1 and 4, the situation is flipped, isn't it? 4 is actually a larger number than 1 is. But when you go to the negative numbers, -4 is actually smaller than -1. And it's because you just got to think about it as being a mirror swap, a mirror flip about the number 0. So in general, we call the less than symbol, the greater than symbol, we call them inequality symbols. If you want an equal sign, that's the equality symbol. 5 = 5. But here, if you're using an inequality sign, you're saying that one number has to be less than the other, or one number has to be greater than the other. And like I said, if you're in Zoom, feel free to get involved. I can see if you're using the text box or not, so you can ask me questions through that. I don't want to just blow through it. Normally what I like to do, because look, 3 hours of straight math, not only with a mask on, is it not going to be just a whole lot of fun from that perspective, but really 3 straight hours of math, it gets tiresome, doesn't it? It gets a little bit grinding. That is absolutely the case. And I teach math, I've studied math, I have a master's in it, and I've done math for my entire life, and even I'm like, okay, I need to stop, I need to do that. So you might see me, whether you're in Zoom, whether you're in person, you might see me kind of break up the monotony a little bit with some humor. How many of you would like that? How many of you would like that? You like a little bit of humor. You like some humor, you like some fun. How many of you in Zoom would like that? Do a thumbs up if that's a thing, or you can use the text box. Yeah, we can like that. Well, here's the truth. I was going to do it anyways, whether you liked it or not, but in terms of humor. But it's nice to know that most of you seem to like that. Also, none of you are going to think I'm funny. You're not going to think I'm funny. That's just how it works. But you're going to fake laugh for me. Okay? Can we all agree on that? You can fake laugh. I can't tell if you're smiling unless you're at home. What's that? Is your grade dependent on it? Not directly. Not directly. Never directly. But, subconsciously, on a subconscious level, it's the end of the semester, and I'm like, all right, let's get in there. And, this person was always laughing at my jokes. Oh, I'm just kidding. No, your grade doesn't depend on it, but your overall experience is definitely greater than if you didn't do it. There you go, math words. See, I used math. How are you guys doing in Zoom? Is everything looking good? Can you hear me, understand me now that we got about 20 minutes in? I just want to make sure, I definitely don't want to forget about you guys, of course. I'm going to assume that's a yes, or they can't hear me when I don't think that is the case. Here we go. Yes, doing great. Awesome. Thank you very much. Cool and groovy. Okay, so What we can do then is we can figure out what symbol needs to go where. So in part A, we're going to put either a less than symbol or a greater than symbol, just based on whatever makes it into a true statement. So -4 blank 3, should I put the less than symbol or the greater than symbol? Absolutely, less than symbol. All negative numbers are automatically less than any positive numbers, any positive number, right off the bat. So I would put a big less than sign. Probably a way to annotate on here, but I don't want to. Once you try to figure out something new, it destroys everything you just did. So we'll take it easy for now. But yeah, in part A, we would use the less than symbol, which is this one right here. Part B, -1 blank -5. It's greater than, exactly. -1 exists to the right on a number line than it does of -5. What if I flipped them? What if I said 1 blank 5? Not right, exactly. So if I had -1 and I had +5, then I would be less than. Exactly. So if this 5 was magically changed to a positive, then we'd have a less than situation. Instead, -1 is actually greater than -5. Part C, -5 blank -2. What are you thinking? Less than, exactly. -5 exists to the left. Here's -5. It exists to the left of -2, thus it is less than. So C is less than. D, 0 blank -3. 0 is greater than -3. That is absolutely right. Because look, here's 0 on the number line. Here's -3. 0 exists to the right of -3. Thus, it is greater than. So we have the less than symbol. We have the greater than symbol. We have a couple other symbols that are going to just kind of fully make everything all come together. And whoops. What we have is we have the less than or equal to symbol, and we have the greater than or equal to symbol. So less than or greater than is strict, meaning 2 has to be strictly less than 9. But 9, which is equal to 9, 9 is still less than or equal to 9. Just think about it logically. 2 is less than 9. 2 then is also less than or equal to 9. Either one works. 9, though, is not less than 9, but 9 is equal to 9, thus 9 is less than or equal to 9. It sounds almost like double talk, but it's really pretty straightforward. What we're going to end up doing is we're going to be substituting variables in. We're going to be using variables. We're going to be using X, we're going to be using Y, we're going to be using maybe some Z's we'll throw in there. A's and B's and C's, everything is going to get a fair go at it. So what we're going to do is we're going to investigate later on, what does it mean for X to be less than 3? We'll talk about that. Absolute value, absolute value, absolute value, absolute value. Let's talk about absolute value. Let's talk about absolute value. If you're taking the absolute value of a number, you're asking how far away is it from 0? Not which direction it is, but how far away is it? So the absolute value likes to use these vertical bars. So if we were to take the absolute value of 3, what that is asking is, hey, how many units away from 0 is the number 3? And it's really not, there's no trickery to it. How far away from 0 is 3? 3 units, yeah, exactly. Think about it. Look on your number line. Here's, we'll put 0 a little over here. Here's 1, here's 2, here's 3. 3 is uno, dos, tres units away from 0. So the absolute value of 3 is 3. Things get a little bit interesting when we take the absolute value of negative numbers. Negative numbers become a lot more interesting. But no matter what, the guiding principle behind absolute value is you're asking how many units away from 0 is this number, and I don't care which direction it is. So what do you think the absolute value of negative 2 is? 2, exactly. It's positive 2 as well. Because, make up our number line. I'll put 0 over here. Here's negative 1. Here's negative 2. So negative 2 is the number we started with there inside the vertical absolute value brackets. And now notice it's 2 units away from 0. It doesn't care what direction it is. Does your car care if you went 45 miles east today or 45 miles west? Does your car really care about that when it comes to the amount of damage you've done to the engine or the wear and tear on the car? Your car doesn't care if it's 45 miles and you drove into space. It doesn't care. Well, maybe it would in that case. You'd care. You'd care very, very quickly. But if you're going 45 miles, either way, you're putting the amount of wear and tear. That's kind of like what the absolute value is. It doesn't care which direction things are going. It's simply saying, hey, how far away is it? And then the trick one, not really a trick. It's actually a lot more straightforward than you think. That looks like a TIE fighter. If you know what a TIE fighter is, you're probably older than 25, or you like Star Wars. There it is. What do you suppose is the absolute value of 0? 0? You guys read it in the text box. What do you suppose is the absolute value of 0? You guys tell me out there in the Zoomosphere. What do you guys think? 0? Well, if you're worried that I was about to say that everyone who answered 0 a second ago was wrong, so you're nervous, don't be worried about it. You're absolutely right, Xavier. It is 0. Not even a trick question. Because how far is 0 away from itself? No units. It's right there. It's on itself. So the absolute value of 0 is 0. Pretty straightforward, pretty straightforward. So, hey, we just talked about all that. Look at me. It's like I know what I'm doing. Okay, here's the part. We're going to talk about addition. We're going to be talking about specifically addition of integers. Positive, negative, whole numbers, or 0. We're going to be talking about them. Now here you see that little rule. It says if the integers have the same sign, add their absolute values. The sign of the sum is the same as the sign of the, what the heck? It's a lot of double talk. There's no way to get around that, unfortunately. So let's not double talk. Let's single talk, all right? And that's freedom right there. When you're adding 2 numbers, let's say you're adding 2 positive numbers. That one is straightforward. 3 plus 5. No trickery. What is 3 plus 5? 8. Ocho. Think about what you're doing on a number line. Here's 0 way down here. Here's 3. When you're adding 5 onto 3, if you add a positive number, so I'm adding 5. You add a positive number, you're saying go 5 more units to the right than where you started. So I need to go 1, 2, 3, 4, 5 there. And that naturally gets me to plus 8, or positive 8, I should say. So I added 5 units onto 3, and you get 8. I think we're all pretty comfortable with basic addition like that. Does that sound about right? Good. Basic addition, because we're going to build everything else on that. So if you're adding a positive number with a positive number, that's the nicest situation possible. Of course, this is a college level math class. Am I always going to give you the nicest situation possible? Very rarely. I'm going to give you the situation from Jersey Shore. Well, he's pretty nice, I suppose. That joke might be a little dated even. Wow, Jersey Shore hasn't been on for a little while. Interesting, interesting. Gonna have to update my joke repertoire. So when you're adding two numbers that are positive, they become even more positive. If you add two numbers that are negative though, negative, I don't know, 7 plus negative 4. I'll put the negative 4 in parentheses just so this plus sign here and this minus sign, you don't get your wires crossed. You kind of can tell what's going on. So what I'm doing is I'm starting with negative 7, which is already a negative number. It's already down on the left side of the number line, left of 0. So negative 7 is already pretty negative. So let's think about what's going on the number line. Now I'll put 0 over here. You can orient the number line however you want. Here is the negative 7 we started with. We're starting with negative 7. Now, normally when you think about adding, you're thinking, hey, I'm bringing more things into the fold. I'm making it bigger, larger, greater than what it was to start with. But things get a little bit flipped when you add, in this case, a negative number. Since I'm adding a negative number, it's really kind of a slap in the face. It's like saying, okay, here's negative $20, which means you owe me $20. That's a slap in the face. So instead of going to the right on the number line like we would normally want, if you add a negative number, you need to go to the left that many units. So let me get my tools out. Instead of going to the right like we want, adding a negative number means we're going 1, 2, 3, 4 spaces to the left. So we'll call that plus negative 4. But as we'll see in a moment, that's almost just like saying minus 4, right? We're taking 4 units away from it, and that's exactly what we're going to see. Adding a negative number is equivalent to just subtracting that number at its value, its face value. So then, if I started at negative 7 over here, and remember, if I went 4 units this way, the number is going to get closer to 0. But if I go this way, the numbers are going to appear to get more extreme. So then negative 7 plus negative 4 is going to be what? Negative 11, exactly. Exactly. So adding a negative number, so here's how it works. If you add 2 positive numbers together, you kind of already have an understanding of that. That's the straightforward one. If you add 2 negative numbers together, you're starting with something that's negative and only making it even more negative. So another way to think about it is I'm adding 2 negative numbers together. That means my result is going to be a negative number. Once I know it's a negative number, then just add the numbers like they weren't negatives at all. Then just take 7 plus 4, which is 11, and then just slap a negative sign back on it at the end. That's all that this little rule here is trying to say. If they have the sign is the sum of the whatever, it's a little bit confusing, but I don't like teaching it that way. That is not the me way. So that's if 2 numbers have the same sign, but let's not limit ourselves here. Let's not limit ourselves. Let's say they have different signs, and we're completely doing addition here. So let's say we start with, how about negative 6 plus 4, you know what? Let's make it interesting. 14. Everyone say, whoa. Please, I need it for my own sake, because it's been a bad week for me. No, I'm just kidding. It's not been a bad week. It's pretty good. So we're adding 14. So always remember, just start with the negative 6. You know where that's got to go on the number line. If there's a 0 here and the negative 6 is over here, I'm starting with negative 6. I'm adding 14. So am I going 14 units to the right or to the left? To the right, exactly. That's the whole kit and caboodle. So 1, 2, 3, 4, 5, 6. So I've gone 6 of those units and now I'm at 0. How many more units do I need to go? 8 more units, exactly. I've used 6 of the 14 up to get to 0. 8 more will get me 5, 6, 7. Well, you get the idea. So -6 plus 14 is going to be 8. Now again, this PowerPoint in the book, they like to explain it in a different way, but it's like, here's a system of rules. And I think it's a little bit more confusing and not exactly intuitive. So let's keep it intuitive. So if I gave you -6 plus 5, you would just move 5 units to the right, starting at -6, but that wouldn't quite get you to 0. You'd still need 1 more unit to get to 0. So -6 plus 5 is -1. And when you're learning this stuff, go ahead and write out a number line. I'm doing it right here. There's no shame in that whatsoever. Don't try to do it in your head if you're not completely comfortable with it. Write yourself a number line and make yourself happy. And then similarly, one last example on that. Let's say you started with 27 and you were adding the number -13. I'll put it in parentheses. The parentheses, all they do is help me group things properly and not get confused. So take a number line. And now you're starting with 27. You notice from how I drew it, we're not going to be going to the right. Because I am adding a negative number to it, I'm actually going to be going to the left. I'm going to be going to the left. And I'm going to be going to the left 13 units. So in a way, you can kind of think about it as subtraction. I take 27 and I take 13 units away from it. And that's exactly right. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, blah, blah, blah. And you can do the math. You'll get positive 14. You didn't have enough units to get you all the way back to 0. So you're still in the positives. So you can almost think about it like this. Equals 14. And that's your final answer on this one. There we go. So now we can comfortably say, hey, we know how to add whole numbers, integers. We'll get to fractions later. Yeah, we're going to be hitting fractions. How many of you are cringing inside when I say the word fractions? When I say the word fractions, people start shaking a little bit. We'll be dealing with decimal numbers, 5.328 plus 17.26 or something like that. We'll be doing that, but for now, we're starting with just whole nice integer numbers. So we dealt with addition. We should also have a basic idea of subtraction. So let's say you started off with 9 and you're subtracting 4. Give yourself a number line. You don't even need to put a 0 on it. You know where the 0 should go, so you don't have to write every number. There's 9. Now, when I think about subtraction, I'm kind of doing the opposite of addition. So I'm taking 9, I'm subtracting, and then the number I'm subtracting is actually positive 4. I'm calling it subtraction, but then I'm saying positive 4 is being subtracted. So I'm taking back 4 units from it, not taking back Sunday, and we're going to move to the left then. 1, 2, 3, 4 units to give you 5. Now you probably mental math that and said 9 minus 4 is 5. Yeah. But I want you thinking about it in terms of moving in this number line business and where do you go, in which direction. Now the way the book likes to teach it, and I think it's a little bit silly, is that you can rewrite this as 9 plus -4. It is the same thing, yeah, but if you already have a basic comfortability with subtraction, maybe we don't get too tricky with it. How does that sound? But either way, you're going to get 5. Now, what else can you do? What other kind of subtractions could you do? Well, my friend, there's all kinds of subtractions. You could do -4 minus -19. Well, some of you are just chomping at the bit to say, Josh, that's just -4 plus 19. This minus sign right here, this minus sign, they come together and they make an addition sign. So it's -4 plus. And that's right. And if that's how you understand it, let's not try to fix what ain't broke. That's what I say. If you understand it that way, I'm not gonna, jump on you. But let's do it from what we said was the definition of subtraction a second ago. You got a number line. You got -4 over here. Now, I am subtracting. So normally when I'm subtracting, I'm thinking I gotta move to the left. But then the number I'm subtracting is itself a negative number, so then it actually is going to the right. It's like I'm subtracting a negative, it's like a double negative, so they undo each other. And that's exactly what it is. I'm not going to the left 19 units, I'm going to the left -19 units, which is saying I'm really going to the right 19 units. That's kind of why you'll see this just be written as -4 plus 19. So now let's actually do it. We gotta go 19 units. So we're clearly gonna surge past 0. We're gonna go 1, 2, 3, 4 units will get us to 0. But how many more units do we need to go? 15, which is exactly why sometimes you can just flip the order and say -4 plus 19 is the same as 19 minus 4. Because we already took 4 of the units away to get up to 0, and there's only 15 units left, blah, blah, blah. And that is the final answer. If you ask me, and you should ask me, because I know everything. That's called omniscient, all-knowing. I know everything. Ask me a question you don't think I'll know. Go ahead, ask me anything you think I won't know. It can be anything. It can be any piece of knowledge in the entire universe. Yeah. Go ahead. Do you have... $1 million, all right. That's it, it's $1 million, all right. See, I know everything. No, I don't know everything, that's ridiculous. Of course I don't know everything. But I do know a bit. So you said MOS code, I know that means that's your job, right? Your job title in the Marines. And then slow down, what did you say it again? I'll try. Okay, yeah, no, I don't know that. I was not in the Marines myself. But, so I don't know everything. That's just a joke. You're going to go to my boss and be like, he says he knows everything. Well, whatever. Okay, so back to where we are. Let's go back to the PowerPoint here. So addition of integers, we kind of already talked about this. Subtraction. Now, the one thing I didn't mention is something called additive inverses. They like to use a lot of big multi-syllable words when it's not always necessary. Additive inverse, it's just what number do you need to add on to get it back to 0. So if you have 18, what number would you add to 18 to get it down to 0? Well, you can't add a positive number, because if you added a positive number, you'd start at 18 and you need to go to the left to get to 0, but you're actually, if you're adding a positive number, you're going to the right on the number line. So clearly, the number you have to add to 18 to get down to 0 has to be a negative number, so you're moving to the left. And then it's just that same value as 18, but with the other sign. If you were starting with -7, what number would you add to -7 to get it to 0? Well, since -7 is to the left of 0, it's got to inch forward to the right to get up to 0, meaning you have to add a positive number to -7. And then the number, it would have to be 7 itself, clearly. So basically, that's what's going on here. The additive inverse of a number is just take that number and flip its sign. You start with -3, its additive inverse is +3. You start with positive 300 trillion, its additive inverse is negative 300 trillion. It's not super complicated, thankfully. So additive inverses. And you can say you learned a neat little phrase. How many of you, or is it kind of warm in here? I think wearing the mask, if you're talking, moves hot air up, and then it makes my forehead warm, which makes me feel warm. But we will suffer through it. Okay, so we've talked about addition and subtraction. Believe it or not, I mean, addition and subtraction, if you're dealing with positive and negative numbers, it can get a little bit confusing. Your wires can get crossed pretty easily. So don't take it for granted, because there's somewhere, it's not as straightforward as you think. That's why I like to teach it on the number line. I want it to be intuitive and not just go remember a bunch of rules. I want you to see why we do it, how it makes sense. Now, multiplication of integers. Well, this course, we review multiplication only in the sense that we talk about how you multiply signed numbers. What do you do if one number is positive, one number is negative? What do you do if they're both positive? What do you do if they're both negative? That's all we cover. The actual theory behind multiplication, we come into this course assuming you know that. So how many of you know what 3 times 6 is? What do you get? Go ahead. 18. Very good. How many of you know what 5 times 7 is? Anyone? 35, exactly. So we already understand the basics of multiplying. All we got to do is deal with signs. So if I multiply 2 positive numbers together, what kind of number do you get out of that? Exactly, you get a positive. If I multiply 2 negative numbers together, what do I get? You also get a positive, yeah. And that actually is not as intuitive as you think. That's one of the few things that we study just by rule. It turns out to prove that that's true, you got to use some heavy hitting math that is a little bit beyond the scope of what we do this. So, yeah, the idea is this. If you multiply 2 numbers that have the same sign, either they're both positive or they're both negative, it always comes out positive. The 2 positives make sense already. The 2 negatives, you can think of it as like a double negative. They cancel each other out and make it positive. If you multiply 2 numbers that have different signs, one is negative, one is positive, doesn't matter which one comes first, your result is going to be negative. But once you've dealt with the signs, once you know, okay, this is what the signs are going to be, just kind of write it at the end. Okay, I see I have a positive number and a negative number, so my answer is going to be negative. Then you can ignore it for a moment. So if I had to do 36 times -5, okay, that's a positive and negative. So I'm just going to go write a negative sign where my answer is going to go. Then I'm just going to go do 36 times 5 for the moment, because it's then whatever I get out of that, then I'm going to put it in there as the answer. And so 36 times 5 is 216. So 36 times -5 is -216. Now, we also don't, in this course, we also don't talk about kind of like long multiplication. I don't know what you'd call it really, because it's just something that is intuitive to me. But like, yeah, if you had 116 times 23, you remember how you do it this way? Exactly. So yeah, exactly right. You might have to carry some things. 3 times 6 is 18. So you put the 1 down here, or excuse me, the 8 down there. You carry the 1 up there. Then you do 3 times this 1, which is 3, plus this 1 up here, which gives you 4. Then you do 3 times this last one. There's nothing carried up here. So you get that. So you've dealt with the 3 first. Now we got to come deal with the 2. But secretly, that's not a 2. That's actually like a 20, isn't it? Because it's in the tens column. So that kind of gives an idea of why when we come down to this next line to deal with the 2, we put a 0 there. And then we deal with the 2 in the same way. 2 times, and now it might help to get rid of that 1 that you've previously carried, because it no longer applies here. 2 times 6 is 12, so put the 2 down, carry the 1. 2 times 1 is 2, plus 1 is 3. 2 times 1 is 2. And then you do addition. 8 over here, 8 plus 0, 6, 6, 2. So, 116 times 23 is really 2,668, and we can do it that long way. We assume in this class that you have worked with long form multiplication like that. But when we get to some numbers like that, especially when we talk about decimal multiplying, I will kind of go through it slowly with you. I'll show you what I'm doing, what I'm thinking. And so that is it. What's really interesting is really 116 times 23. What we really do is we do a little trick with the distributive property. We say that's 116 times 20 plus 116 times 3. That's actually all we're really doing. And so whatever you get here, you add it for what you get here, but that's what each of those rows were that we just did a second ago. And that's also why we carried a 0 earlier. So just a neat little thing for you to remember. Back to it. Now finally, so we talk about basic multiplication. We're going to cover division in a little bit, because division is kind of special. Division has its own little interesting quirks about it. Exponential notation. We talked about exponential notation last time when we were doing prime factorizations of numbers. Remember last time I said, well, here I'm doing 2 times 2 times 2. I've got 3 2's going on, so I'm just going to write that 2 to the 3rd power. That's exactly what it is. So, no, not there. So if you're doing, say, -6 squared, it's a negative number. You're saying, okay, take this base, -6, and multiply it to itself 2 total times. Don't do -6 times 2. That's not what we're doing. We're saying take -6 and multiply it to itself 2 total times. Boom, boom. You multiply a negative to a negative, you get a positive. 6 times 6 is 36. So -6 squared, where you put the negative inside the parentheses, comes out to positive 36. Now this is confusing, isn't it? You just said -6 squared is positive 36. Then you come over here and say -6 squared is negative 36. This is one of those rare cases where you have to be careful about how you verbally say something in math and what you really mean on paper. In this first case, you're saying take the number -6, the negative sign and everything, and square it, multiply it to itself. In part B, you're actually, according to order of operations, you're actually saying, no, do the 6 squared first, then slap a negative sign afterwards, which is why this is going on. So by putting it in parentheses, you're applying the squared to the whole thing. Without the parentheses, you're only applying it to the 6 and then slapping the negative sign on later. And then you see -5 cubed is -125, because these two are going to become positive, but there's an odd man out who's going to make the whole thing negative. Down here, -2 to the 4th, this becomes a pair and they're positive. This becomes a pair and they're positive. So the whole thing goes positive. So when you take a negative number, like -5 here, you take it to an odd number power, your solution is going to come out negative, because there's always one odd man out that makes the whole thing go negative. If you take a negative number here and you raise it to an even power, an even number 4, then there is no odd man out. Everything's going to pair up and everything's going to become dandy and positive. So real quick, let me take attendance and then we will take our break. How does that sound? So we're still here in the Zoom room. I'm not going to close the Zoom room or anything like that. Desi Drake, I see you're here, so I'm marking you as online attendance on August 27th. Esmeralda, I see you're here. Justin, I see you're here, marking you. Nicole, I see you online. Xavier, I see that you are online as well. And yes, I got everyone online. Okay, in person, Slater. And I promise I will try to have your names good. If you're on Zoom, I already took your attendance, so you can just go hang out. I'm going to pause the recording. Okay, so we just talked about exponential notation for things. Now we're going to be talking about division of integers, division. And again, it's kind of weird because we're going to talk about division, but we kind of come in assuming you already understand the basics of division, specifically long division. Now down the line, there will be moments where I will sit down and do some long division with y'all. But let's see here. So whenever you have one number being divided by another. So this is great and all, but let's do it my way, as Frank Sinatra liked to sing about. What we're really going to say is, say you have 3, you're dividing it into negative 12. The result is going to be negative 4. You'll notice that's the same as doing this. Or you can say negative 12 divided by 3 equals negative 4. So those are all kinds of the different ways that we can symbolize division and how we actually perform the process of it. Let's talk about a few labels. Now, if you are a little bit younger, you probably don't like labels. As you get a little bit older, you just realize they're convenient. So whatever trips your fancy. So the 3 in this case, and in general, the thing that is doing the dividing. Negative 12 is being divided by the 3. The 3 is called, does anyone know? We kind of talked about it last time. The divisor, that's exactly right. The divisor. That is what the positive 3 is. Now, no one is probably going to get this one, and it's not really on you. Does anyone know what the negative 12 would be, and why is that not in blue? Yeah, good job, good job. Not super important to know that, but it's cool if you happen to know. This is called the dividend. It is what is being divided. Again, it's not ultra important. That's not a term we're going to use a lot. But then probably the most important term, let's use green. Green. You have to select the color last. There we go, green, negative 4. Does anyone know what that thing's called up there? The Q word, it's quotient. That is the result of dividing. The quotient. That's going to be important a little bit later on when we talk about some of the key words and key phrases that we use to say, okay, this is an addition problem, this is subtraction, this is multiplication, this is a little bit of both, bada bing, bada boom. So back on to it. There's some rules here, and look at that page. It's you know, they're doing the best they can, but there is a few rules that we want to remember. They're very similar to multiplication. Because actually, here's a little hint. Addition and subtraction are the exact same thing. It's just telling you to move this direction on the number line. Multiplication and division are also secretly the exact same thing. It's just division can be thought of as multiplying by a fraction. If you divide by 9, you can say that's the same as multiplying by 1 over 9. It's 6 of one, half dozen of another. So, as we can see here in this first rule, basically, if you have one number and you're dividing by another number, if one number is positive and the other is negative, then just like multiplication, the result is going to be negative. It's because division is just the the opposite of multiplication. If you took 80 and divided by -4, what you're really truly asking is, what does -4 need to be multiplied by to give you that positive 80 on top there? That's what division is. And the answer has to be then negative, so that the two negatives cancel out to become that positive 80. So it's just two different ways to think about it. So if you're doing division, one's positive, one's negative, the result is negative, just like for multiplication. And similarly, if you take a positive number and divide by another positive number, you'll get a positive number. If you take a negative number, divide by another negative number, you'll get a positive number. It's almost like the signs cancel out, in a way. Now here's some interesting things. Here's one here at the bottom that is kind of cool. If you take 0, you cannot divide by 0. That's rule 4, and we'll explain why in a second. That's such a special case in math, it deserves a minute of its own time. But you can divide 0 by another number. 0 can be the dividend. It cannot be the divisor. But 0, you can divide 0 by -5, and yeah, it just comes out to 0. But you can never divide by 0. Look here, -8 divided by 0 is undefined. When I say undefined, I don't mean the answer is 0. I mean there is not an answer. There's no number that you can apply here that is going to satisfy that. So now, let's look back at the whiteboard. And you're bad. Let's talk about why you can't divide by 0. Why doesn't it make intuitive sense? Let's use, for a starting example, let's use something simple. Let's say you do 12 divided by 6. What is 12 divided by 6? You can type it in the text box if you want. No trickery, I promise. What's 12 divided by 6? 2. Very good. 12 divided by 6 is 2, because if you cut 12 into 6 equal size slices, you have 2 or whatever. However you want to think about multiplication. So that's one way to think about division. You say, okay, 12 divided by 6 is 2, but another way to think about it is, okay, pretend you didn't have that 2 there. All right, 12 is the number that's being divided. 6 is the thing doing the dividing. When you say 12 divided by 6, and I want everyone to close their eyes, because it's fun. Do it at home too, on the Zoomify. Close your eyes. When you take 12 divided by 6, you are saying 6 times what mystery number that I'm looking for, 6 times what number gives me the 12 I started with. If you think about division that way, at least for simple numbers, it's pretty simple as well. So you say, well, I have to multiply 6 by 2 in order to get 12. And thus, you can open your eyes now. Thus, the result of 12 divided by 6 is 2. It's got to be. Let's think about 0 now. Let's think about 0 as a special case. Let's say you did 0 divided by, I don't know, 4. Use the same reasoning. 0 divided by 4. You're asking for this number on bottom needs to be multiplied by what mystery number in order to bring it to 0? 4 times what is 0? What's the answer? 0, exactly. So I can have 0 on top and a non-zero number on bottom. Any number I want on bottom that's not also 0. I can do that, and the answer just happens to be 0. It's kind of intuitive. We kind of have that idea. Now, using the same motivation, how come we can't divide by 0? Well, let's look at that. I'll use red to say bad. Let's say you had 11 and you were dividing it by 0. 11 divided by 0. How many of you, before you knew coming into this class, you would have said 11 divided by 0 is equal to 0? How many of you, be honest, you can be honest, you probably would have thought that, right? And yeah, that's totally fine because that's kind of almost intuitive. You usually think if you're dealing with the number 0, then the answer is going to come out to 0. But it's not. Let's talk about why. When you take 11 divided by 0, you're asking what number gets multiplied by this 0 on bottom? What mystery number is going to get multiplied by this 0 to produce 11? Is there anything that's going to work? Nothing works. Any number you want to multiply this 0 by is never going to give you 11. It's always going to give you 0, isn't it? It's never going to get you there. So saying 11 divided by 0 equals, that alone is a silly idea. There is no answer. I can't say it equals anything. There's no answer. There's no number that's going to work and make that happen. We call that undefined. It literally doesn't have a definition. There's nothing we can do with it. And then one more interesting case. How many of you thought that's actually kind of interesting? How many of you were like, oh, okay, yeah, that makes sense. Or how many of you will pretend that you think it's interesting in order to placate me? Anyone? Anyone? Okay. Maybe out in the Zoomosphere, you guys will try to make me happy with just pretending like I'm saying interesting stuff or pretending that I'm funny. Pretending that I'm funny is going to be the real path to my heart if you really want to know. But now it's starting to dawn on me. Maybe I'm not funny. Maybe I've spent my whole life thinking I was funny and people were just BSing me. Oh man, I'm having some major life revelations now. Just playing around, not having any major life revelations. One last interesting case. What if you took 0 and you divided by 0? That is one of the most interesting cases in there. Let's think about it. You would think that it's okay. You think that it's okay. Because what you're essentially asking, according to our earlier thought, is what is this bottom number, 0, need to be multiplied by to get this top number, which also is 0. Someone give me a number that'll work. 0 itself, yeah. If I take 0 and I multiply by 0, I get 0. So you're tempted to say, I can do 0 divided by 0. Someone give me another number that's going to work. 7. 0 times 7 is 0. That works as well. 4 works. 0 times 4 is 0. Uh-oh, we have the opposite problem. In the last example, dividing by 0, there's nothing that would work. 3 divided by 0, there's nothing that on the planet that'll work. Here we have the opposite problem. Here, 0 divided by 0, there's an infinite amount of things that could work. That's a different kind of problem. But it's a good problem to have. But at this level, we're not going to stress over that. We're still just going to say that's undefined. We're going to say that's undefined, nevertheless, 0 divided by 0. So, we have 0 divided by 0. We can't divide by 0 in general. It's going to be a no-no. It's going to create just too many issues. So don't do it. Next up, we can talk about order of operations. Order of operations. Let's see if I can just draw. Nope, doesn't like it. Never mind. So order of operations. Let's say you had something nasty. Look at that. How many of you are going, ooh, in your mind? 6 squared minus 24 divided by 2 squared times 3 plus 1. What the heck? How do I know where to start? And how do I know what to do first? How do I know what to do second? That's exactly what the order of operations is. We are giving ourselves an order in which to do things. And it's not always just go left to right. That's not always what it ends up being. In fact, it almost never ends up being that. So one way to think about order of operations, there is a classic mnemonic device, which is something that helps you remember. There's a classic mnemonic device. How many of you remember what it is? PEMDAS, exactly right. PEMDAS. PEMDAS, sometimes it's called. To remember in your head, you might remember it as, please excuse my dear Aunt Sally. That's fine if that's how you remember it. Remember, memory devices don't have to be cool, they just have to work. If it helps you, it can be as corny as you want. but if it helps you and it works. So please excuse my dear Aunt Sally. This is the order. You go from top to bottom. And so the order is to do things that are inside of parentheses first. And to spare you from my handwriting, let me use the text box. You guys in the Zoomosphere will thank me for that. So the first one is parentheses. Next up, you take care of any exponents. Third up, you take care of multiplication. Also third up, you do division. You count multiplication and division as basically the same step. Then you do your addition and subtraction. That is the order of operations. Let me explain it a little more. I'm going to put lines here. There's really only 4 steps. You do your parentheses first. What does that mean? That means anytime there's an operation inside of parentheses, even if it normally shouldn't come first, by putting it in parentheses, we're saying no, make that the first thing. So if you had so you had that 3 times 4 squared times 2 plus 7 in parentheses. Order of operations says do what's in the parentheses first. This gets taken care of first there, Pilgrim. You do that one first. So I'm actually going to do the 2 plus 7. Normally that doesn't seem right because addition and subtraction should come at the end, but the parentheses make it, it's almost like giving something an exception. So I do that 2 plus 7 first and I get 9, and everything else stays there, times, basically in parentheses, 9. Now I'll keep the parentheses around it, but basically the first step is taken care of. We've done every operation we can that's inside of a set of parentheses first. Now that that's done, we've taken care of parentheses. Now we got to do exponents. This is the only exponent I see. So first, what is 4 squared? 16, because you do 4 times itself. You do 4 times 4, exactly. So then I'm doing exponents next. 3 times 4, I haven't even touched multiplying yet. And I'm sorry, that's 16. So I can cross exponents off the list. Now I do my multiplication and division, and then I need to do this from left to right. So you start with the leftmost, you do any multiplication division, but you treat them as the same. So it's 3 times 4 divided by 7 divided by 6 times 3. You just do the multiplication, then you do the next division, then you do the next division. You don't do all the multiplication first, then all the division. You don't do that. You do it, you treat it like it's the same thing. Treat like it's the same thing and go left to right. On that bad boy. And so that would let us take care of the last problem here. Now that one, the numbers are going to get a little bit nasty. We'd have to do 3 times 16, which is 48, and you can do it by hand. You can use long form multiplication. Then we got to do 48 times 9. Well, I know 50 times 9 is 450. I take 18 back from that. It's going to be 432. But you can do that by hand. Should you do it by calculator? I mean, you'd like to do it by calculator. For the purposes of this course, remember, the developmental portion, the 0332 portion of the course that we're starting with, we're not using a calculator at all. So I can't tell you what you're going to do on your homework, but if you use a calculator on your homework, you're just tying your own hands. Because come exam time, you can't use the calculator. Remember, our exams will be monitored. And I can see, plain as day, oh, you got a calculator in your hand. So, no calculators. So 432 is it. Now I gotta go undo a whole bunch of stuff. going back in time here. There's probably an easier way. No, there's not. Whatever. Life goes on. So please excuse my dear Aunt Sally, the PEMDAS. That's going to be it. So it's parentheses, exponents, multiplication, division. Think of it as one step, addition, subtraction at the end. So let's try out this guy. 6 squared minus 24 divided by 2 squared times 3 plus 1. Remember your order of operations. Imagine your wise old teacher, maybe what's the little green guy's name from the Star Wars movie? Yoga? Yoda. I know, I'm just messing with you. I'm a big Star Wars nerd. Yeah, imagine Yoda speaking in your head, and he says, hey, I'm Yoda. I'm the guy Yoda. Remember to do the P's, excuse my dear Aunt Sally. He says that. He says, remember to do the PEMDAS. The P is for parentheses. Do you see any parentheses in this particular example problem? No. So do you have to worry about the P in this one? No. In general, you would, but not here. So whatever, skip the P, go to the E, exponents. Do you see exponents in this problem? 2, exactly. I see this one here and this one here. I need to take care of those exponents first. So that's kind of where you can follow along here. The exponents happen first. 36, this 6 squared became 36. 2 squared became 4. So we took care of the exponents first, and now we're at this line. Now exponents are done. Next up, multiplication, division. Remember, we're thinking of them as the same thing and just going from left to right. So we have 36 minus 24 divided by 4 times 3 plus 1. We got to take care of that stuff in the middle. We can't do the 36 minus 24 yet. So first we do 24 divided by 4, we get 6. Then we do the 6 times 3, we get 18. Does it make sense how we got to there? Everything straightforward, left to right. And now we just do the addition, subtraction from left to right. 36 minus 18 is 18. Add that 1 back on, we get 19. 19 as our final answer on it. Okay, so that covers it for that section. Let me pull up my next set of notes. And the internet is being really slow right now. And now we have a big one. We are going to deal with everyone's favorite F word in mathematics, fractions. 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 Wait a minute, Josh. Someone say, wait a minute, Josh. The closest you have to say. Wait a minute, Josh. You just said we're doing fractions, and then you're telling me about these things called the rational numbers? Well, it's time to expand our vocabularies a little bit. A fraction is just another word for a rational number. And you'll notice that embedded in there, inside the word rational, is the word ratio. Ratio. When you think of a ratio of two things, you naturally think about division. And fractions are just so it all kind of makes sense. It's not do anything wonky. How are you guys doing out there in the Zoomosphere? Just want to make sure you guys are okay. Just drop a little something in the chat box saying, hey, we can hear you, you're good. Great, very great to hear that, doing good. Awesome, thanks guys. Just want to make sure we're hearing me and there's no technical issues. Okay, so back to it. We are talking about the rational numbers. And all right, so this is where things are going to get a little bit, not difficult, but just you got to expand your mind a little bit. A rational number is any number that could be expressed as a fraction. That could be expressed as a fraction where the top number is an integer, where we defined the integers earlier. The bottom number is also an integer, with one exception. What's the only number? What's the number you can't divide by? 0. So we put a restriction. We say, okay, the top and bottom have to be integers. 0 is an integer, so we'll make one exception. The bottom shouldn't be 0. Can't be 0. The top number can be 0. That's fine. So put another way, the rational numbers are the set of all, basically, fractions. That's a good way to think about it. So earlier, let's talk about the symbols we've used. We used that weird script N to be the natural numbers. Natural, positive whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Integers, we used a weird Z for the integers. The N makes sense, N for natural. Z, it actually comes from a German word, the word Zahlen, which means number. So German mathematicians kind of crafted that. I just gotta make sure my dog doesn't get double fed. I mean, he'd love it, but you know, he's on a diet. Okay, so the integers use a Z. The rational numbers really use a Q, and then there's just some special line there to symbolize it. And these are called, this is the set of rational numbers. Someone say, Josh, why are we using a Q? Why are we using a Q? Thank you. Remember earlier when I talked about division, I said the result of division is called the quotient? We use Q for quotient when we talk about the rational numbers. We're saying it's all the quotients, if you will. That's why. So we use a fancy script Q to represent the rational numbers. And we remember the rational numbers, the set of all fractions, or to be more careful, the set of all numbers that can be expressed as a fraction, where the top number and the bottom number are both integers, except you can't divide by 0. So let's play a little game. Let's play a little game. You guys at home, you can play too. Everyone in class, you are free to play this game with me. If you're at home, use the text box. Let me know if the following numbers, I'll do them one at a time, are rational or not. All right, vote now. You can use the text box. Is 1/3 rational? Is it a rational number according to this definition? In class, what are you guys thinking? Sure. Yeah, that's exactly right. That's exactly right. We got the messages flowing in. Yes is the correct answer. 1/3 is indeed a rational number because it's a fraction, but more importantly, it's a fraction where the top and bottom number are integers. So 1/3, ding, rational. Next number, -117 over the amount of money in my bank account, $4,507,856. That is not the amount of money in my bank account. But is that a rational number? What do you guys think? Out there in the Zoomosphere, you can share with me in the text group. Well, a rational number just has to have an integer on top and an integer on bottom. Is negative 117 an integer? Yeah. So Nicole, you are correct. Xavier, you are correct. Both the top and bottom are integers. It doesn't matter. I mean, integers can get really large really fast. So both the top and bottom are integers. So this is a rational number. It's a rational number. Let's do a couple more quick ones. How's about we try 31.2, that's bad, 31.2 over 7. You're thinking no. What about you guys out there in the Zoomosphere? Is that a no or a yes? Well, we remember the rational numbers. Yeah, you got it. It is a no. Because the rational numbers, it's got to be one integer divided by another. And 31.2 is not an integer. An integer has to be a whole number that's positive, negative, or 0. You can't do any halfway in-betweens or anything like that. So that's not rational. Now let's do ones that are going to look difficult but are real straightforward. Let's use pink. How about the number 10? 10. Be ye not fooled, because a rational number is just a number that could be expressed as a fraction. It doesn't mean it always will be, but could you write it as a ratio of 2 integers? Yeah. You could write 10 as 10 over 1 if you want. Maybe you're bored someday and you decide to turn it into a fraction. You can do it. You can write 10 as 150 divided by 15. They're all representations of the same number. So any integer, positive, negative, or 0, any integer that's not even written as a fraction is still a rational number because you could write it as a fraction. You could write it as a ratio of 2 integers. So that is, and finally, the last one, 0. That's a very bad 0. It looks like a Pokemon or something. I don't know. There we go, 0, the final countdown. In the Zoomosphere class, is 0 rational? Could you write it as a ratio of 2 integers? We do know 0 is an integer. We've already defined it as one. And it turns out, what do we got in the chat box? Come back to me. Ah, that's the tricky one. You want to say it's not rational, but it is. Because it just has to be something that could be expressed as a ratio of 2 integers. And you can. You can do 0 divided by 3. You can't divide by 0, but 0 can be the thing getting divided. So since I could write 0 as 0 over 3, I could write it as 0 over a trillion if I wanted to, or just 13. Who cares? Yes, 0 is a rational number. That actually makes for a really interesting picture. Any integer, positive, negative, or otherwise, you could always just slap it on a fraction over 1. That's the same number. Which means any integer is automatically also a rational number. 0, positive integers, negative integers, they're all rational. That creates kind of an interesting relationship that we can already start to see forming. We start with the most basic set of numbers, the natural numbers, with that fancy script N. No, we'll leave it alone. The natural numbers, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, blah, blah, blah. What's the largest natural number? Trick question. There isn't one, exactly. There's no largest natural number. So there's still an infinite amount of natural numbers, but they're the most basic, simple ones. Then nestled, or the natural numbers are nestled inside the set of all integers. The integers are all positive numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that are whole. The integers include 0. The integers include all the negative numbers. But that means every number which is a natural number. If you're in this circle, you're also concurrently in this circle. In other words, all natural numbers are integers. That's a cool relationship. When we get further along in this course, we will use the term subset. We'll say the natural numbers are a subset of the integers. Question time. Question time. Are all integers natural numbers? Is the reverse true? No, exactly. Very good. No. All natural numbers are automatically integers, but just take -5. -5 is an integer, but it's not natural. So -5 would exist somewhere in the outside area. Very good. Then, remember we argued, okay, all natural numbers are integers. We just argued that all integers, you could slap them over a 1 and call it a fraction. Thus, all integers are also members of the rational numbers. So, both of these then are completely nestled. Oops. Both of these are nestled inside even another set, the rational numbers. The fancy script Q. My dog almost got double fed. My girlfriend almost fed him again. And I said, he shall only be fed once. Thus declareth me. So he's not going to get double fed. He's probably going to be mad at me when I come home. And we're going to talk, because I talk to my dog, and he responds back to me, and I'm seeking some help for that. How mad's your dog? Oh. It's like, do you even love me? Sometimes love means making hard decisions. So, back to it. All natural numbers are integers. All integers are rational. All natural numbers, by extension, then are also rational. Are all rational numbers integers? No. 4/7. 4/7 is rational, but it's clearly not an integer because it's not a nice, clean, whole number, is it? It's between 0 and 1. So you can go one way, but you can't go the other way with it. Now, what we're going to learn in a moment, we're going to learn, or not, perhaps not today, we won't get to it, but we're going to learn that there's another set of numbers floating out around there called the irrational numbers. Irrational. They almost look like Q, but they have a little C up there. Don't get caught up in that notation for the moment. There's the irrational numbers. We'll discuss the irrational numbers in detail next time. What exactly they are, how do you deal with them? But the irrational numbers are exactly what they sound like. You put the ir at the beginning, you're saying the opposite of rational numbers. That's exactly what they are. The irrational numbers are all numbers that are not rational. So there's no overlap between these. There is no number that exists which belongs in this box and this box at the same time. That's impossible. But then all together, when we put them all together into the same, we talk about them, the label that we use, we call these let me get my text box up. We call these the real numbers. Not of Detroit or Atlanta, just the real numbers. So any number which is rational, any number which is an integer, any number that's natural, any number that's irrational. All of those are still in the large overall family called the real numbers. And if you're curious, the real numbers use this fancy symbol, a script R. We'll talk about what the irrational numbers are next time. We're going to keep talking about rational numbers because there's still a lot of interesting things we have to do with rational numbers. Remember, rational numbers can be, they're fractions. So there's all kinds of things we can do with fractions. We can add them, we can subtract them, we can divide them, we can multiply them. And so that's what we're going to have to cover now. You've probably already dealt with this. Don't let the language and terminology confuse you here. This is just saying that there are two numbers that can be written differently as fractions, but really are meant to be the same number. They are the same number in spirit. So for instance, you can have like the number, I don't know, we'll make something up. How about 8 over 4? Now, if you think about a fraction, you're thinking 8 over 4 means 8 divided by 4, right? So 8 over 4 could be just 2. But you could also write that as 10 over 5. You could write it as 6 over 3. You could write it as 500 over 250. All of those are different visualizations of the exact same number. It's just a semantic difference. And then ultimately that number is 2 over 1, or just 2. So in simplest form, meaning lower it to where the numbers are as small as possible, but still the same number otherwise. In simplest form, 8 over 4 is really the same as 2 over 1, or you could just call it 2, depending on your fancy. There are times when you want to call 2 over 1, maybe because you got to do some math with it. And so, of course, you could have something else like 16 over 6. Well, if you remember how to reduce fractions, it looks like the top and bottom can both be divided by 2. So you divide by the top by 2, you get 8. Divide the bottom by 2, you get 3. So 16 over 6 is the same fraction as 8 over 30. In spirit, they're the same exact value, the same number. They just look different. But what we would say is that 8 over 3 is really put into simplest form, because you can't get any lower than 8 over 3, can you? And keep the same true spirit alive. Are you guys kind of liking this system? We have the words on here, so I don't have to write out everything, but I also have a whiteboard so I can show you what's going on. Do you like this system? Normally, I would love to just be walking along the whiteboard the whole time, but that webcam I had set up last time, it just doesn't get the full whiteboard. It just didn't make a whole lot of sense. The audio was trash. So by doing it here, standing here, you guys, I can keep my voice staying right by my computer so the audio is better. I'm not moving around. So is this pretty fair? You guys doing good with this? And obviously, please feel free to ask me questions in the chat box. You guys are chatting with me. You guys say yes. You say I really like it this way. I do too. If let me know later. Shoot me an email if you did see if there was any technical issues or there were times you couldn't hear me. The nice thing also about this way is I'm recording this and I'll be uploading it to my YouTube channel later today or tomorrow. It should show up, so you can watch it later as well. But you can only get counted attendance if you were there live, either in person or on Zoom. Good. I'm glad you guys can hear everything. So I'm a problem solver. You come in with me and there's a problem, let's fix it. Technical issue, let's fix it. How do you fix technical problems? You Google it. That's really all it is. So, very good, very good. So, there are some methods to reducing fractions. Let's try it out ourselves. What you can do to reduce a fraction is you can write out the prime factorization. So, let's say you have 130 over 455, and this is important. 130 over 455. And we want to reduce that. There's a couple methods you can do to reduce it. For one, you can tell they're both divisible by 5. You see, because there's a 0 divisible by 5, meaning I can divide 5 out of them cleanly and still get another integer. Because this top number, the 130, ends in a 0, the bottom number ends in a 5. So a number is divisible by 5 if the last value in it, the ones column, is a 0 or a 5. So I could do that, and then it'll get a little bit simpler, and then there might be more I could do. Or I can do a more direct approach. Here's what I propose we do. I say we find the prime factorization of each number. Remember, there's not one way that you have to do to find the prime factorization. So first off, 130. What are two numbers other than 1 and 130, because that's not interesting? What are two numbers that can be multiplied to make 130? Well, let's think. 130, you got a 0 at the end. So 130 is definitely divisible by 10, isn't it? Yeah, it's definitely divisible by 10. And then what would the other number be partnered with it? 13, exactly. That's the cool thing about multiplying, dividing by 10, is it usually just involves you either moving a decimal point or shaving off a 0 at the end, something like that. So 130 can be broken down into 10 and 13. Now, we need them to be prime numbers at the end. Now, 13 is prime, isn't it? Yeah, I can't think of two other numbers other than 1 and 13 that multiply to 13. But is 10 prime? N to the O, 10 is not prime. What are two numbers other than 1 and 10 that multiply to 10? 5 and 2, exactly right. I'll write the 2 first, doesn't matter. So ultimately, here's all the primes, 2, 5, 13. This means that 130 can be written as 2 times 5 times 13. Everyone say, ooh. No one say, ooh. There we go. See, you guys do follow my directions. So yeah, we can write it as 2, 5, and 13. You erase. There we go. Now let's deal with the bottom number, the 450. 455. That's probably what a 4 for 4 comes out to at Wendy's after tax. How many of you know what the 4 for 4 is? That's a deal. You get a junior bacon cheeseburger, you get chicken nuggets, you get fries, you get a drink for $4 plus your tax. Huh? Isn't that a deal? Am I being paid by Wendy's to say that? Am I secretly just a plant by the Wendy's Corporation? They say, all right, let's just get everyone teaching in the colleges and the schools, and they're just working for us, and they're just telling them to go to Wendy's. Yeah, I am, and I'm proud of it. I am so proud of it. That's not true at all. None of that's true. So 455, what are two numbers that can be multiplied? Well, this is where you have to deal with divisibility. There's a few tricks of the trade that we can talk about. The ones column number here, the 5 at the end, if that's a 0 or 5, that means the number overall can be divided by 5. And that's going to be the key to unraveling this. So I can tell you that one of those numbers is 5. How do I get the other number? What am I going to have to do? Well, exactly right. We need to divide 455 by 5 because we need to know what does 5 get multiplied to give me the 455. So, maybe down here. And you can see if you do the long division, I'm sorry, that's a 1 at the end. So we got 5 and we got 91 now. Now, how many of you are tempted to say 91 is prime? You might be tempted to say that. It turns out it's not going to be prime. How do I know? Well, if you remember your 12 by 12 multiplication table, 3 times 4 is 12. 5 times 6 is 30. 5 times 9 is 45. 7 times 8 is 56. If you remember your 12 by 12 multiplication table, you'll remember that if you go along the sevens, you'd get 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84. You go one more, you're going to get 91. You do 84 plus 7, you'll get 91. So 7 times 12 is 84. If I go one more time, I'm going to get the 91, which means that 91 can be written as 7 times 13. So now we got these prime numbers, 5, 7, 13, all of those are prime. Which is again why it helps to know what the first like 6 to 10 primes are. 2, 3, 5, 7, 11, 13, 17, 19, 23. It helps to know what they are, so you know if you're done. So we're going to write this 5 times 7 times 13. And now there's a cool trick we get to do. It has to do with the fact that everything stays true in ratio, but basically if I'm multiplying everything on top and everything on bottom, I can just crissity-crossity out like this. That's not so bad, is it? Things cross out. Now, hold your horses there, Pilgrim. If you try to say that's 2 times 5 plus 13 on top, no, that doesn't work. All that crossing out we just did does not fly. It only works because everything was just being multiplied. And now the leftovers, all we've got left is a 2 on top and a 7 on bottom. And I know it's in the simplest form because there was nothing else to cross out. Once I put the prime numbers all down there, anything would be completely gone by this method. So using the prime factorizations like this is kind of the best method overall because it's exact. There's no more I can possibly do. And so, look at that. They end up as the same thing as me. I hate mixed numbers and improper fractions. We'll talk about it. I won't go too wild with it because in real life, nobody cares about using a mixed number. Nobody's like, oh yeah, what is a mixed number? Okay. This number here is the number 3 4/5. It's not 34/5. It's not 34/5. Nothing like that. It's not 3 times 4/5, which is why it's confusing because you naturally want to multiply them when they're written next to each other, but you have to resist the urge. This is called a mixed number, mixed because you have an integer mixed together with a fraction, but they're all the same number. They're all together into one number. You wouldn't. Well, it's helpful, and that's why I don't like mixed numbers, because it's like just use an improper fraction. An improper fraction is just one where the top number is greater than the bottom number. So like 25/7. But who really cares if the top is greater than the bottom? It's not wrong. It's just most people don't like that interpretation. The reason that they use mixed numbers is because you may not know that 25/7, well, 21/7 is 3, 28/7 is 4. So 25/7 has to sleep somewhere in between 3 and 4, doesn't it? So I knew if I put it as a decimal, it'd be 3 point something. You may not know that just from looking at the mixed fraction or from the improper fraction. You may not, so like if you had 156,221 over 3,600, you may not know exactly what that number is. But if you converted it into a mixed number, you could say that it's, 4 and 1/10, or I don't know, whatever it would end up being. You see what I'm saying? So you at least know what the first number before a decimal point would be, so you get a ballpark of how large it is. That's really all the whole reason they do mixed numbers and they convert them out from improper fractions. For me, I'm not too keen on that. I don't care. Because besides, we're going to have to do division in order to get fractions and to figure out decimals. So mixed numbers and proper fractions, I will rarely do this because I don't like doing it. There might be a few homework problems over it. There won't be exam problems on converting between the two because I don't think it's a useful skill anymore. I think it's just in math textbooks because it's always been. And no. The other stuff we've talked about today absolutely is useful, but this is a little bit less useful. It's not horribly difficult, but it's not fun. So mixed number improper fractions, converting between them, that's something I'll have you kind of investigate on your own. Remember, you have access to the textbook. You have access to the notes. I'm just going in order. The order you see of your homework assignments on MyLabs Plus is the order I'm going to be going. For the most part, it'll say this is section 5.3 in the textbook, which is exactly what this section is that we're covering. So let's do this. Let's ease into our schedule. Let's call it for today because it's kind of warm in here, and we'll ease into it. So we're getting out a little early today. Next time we'll go a little bit longer, and then we'll kind of stick with that schedule going forward. So remember, we'll start at about 12:35 and go till, about 3 to 3:05 normally, but today we're calling it early. Remember, you can attend virtually or not. You can only attend in person on your day based on your last name of the alphabet, or if you've worked something out with me. I've already taken attendance. I'm going to go ahead and stop recording. And you guys have a wonderful weekend. Thank you, everyone in the Zoom sphere, for coming out. I took your attendance already, so you're good to go.